Hello and welcome back to today's AutoML lecture on neural architecture search with the focus on going beyond simple search spaces. The motivation for today's lecture is that existing NAS methods have achieved impressive results, which we talked about several times or in the last videos, however, mostly on narrow and handcrafted search spaces. And there exist some studies which show that on many benchmarks, random search performs on par with sophisticated NAS algorithms as Bayesian optimization evolutionary algorithms. This raises a fundamental question. So are we searching in the right space? And then the key question we want to talk about in today's lecture is how can we design more expressive search spaces that enable NAS to discover genuinely novel architecture. So we mentioned already that random search can be on par with sophisticated approaches. The paper by Yu et al. From 2020 actually states that, on average, the state-of-the-art NAS algorithms perform similar to the random policy, which is based on the fact that most existing search spaces are kind of limited and narrow with many high-performing architectures. So most of the search spaces we actually work on are cell-based search spaces, which do not differ that much, are rather limited and narrow. And most of the search spaces are actually based on convolutional neural networks, which was kind of based on the fact of when neural architecture search became very popular, that was with the rise of convolutional neural networks, but they kind of still are based on convolutional neural networks, while deep learning actually moved from CNNs towards transformers, for example. One of the other papers which I want to mention is the AutoML 0 paper from Real et al. In 2020, which presents AutoML 0. So the overall idea in AutoML 0 is to automatically search for the whole machine learning algorithm with only simple mathematical operations as building blocks. So we do not search for complete neural networks as building blocks, but simple mathematical operations. And the goal in AutoML 0 is to find the complete pipeline, the model, the optimization procedure, and initialization, in a rather fine-grained search space, which kind of still permits less human design, but allows also to search for non-neural network algorithms. So it's actually just like, what can we achieve using automated machine learning approaches in order to design a complete neural network? And therefore, the search space can become rather large, but kind of fine-grained. And in a large search space, the actual search strategy is rather important, and it's hard to find good architectures in large search spaces. So what we can see here on that image is on the x-axis, we can see the task difficulty, which is kind of calculated by, so the difficulty is calculated by saying, what is the density of acceptable algorithms in the search spaces using long random search experiments. So the longer we need random search experiments and the less acceptable algorithms the random search approach actually is able to find, the more difficult is the actual task. And on the y-axis, we can see the relative success rate of using an evolutionary search approach divided by the random search success. And so here we can see 4 different tasks. The discovery of a full algorithm versus only the learning on the linear or affine regression data. So we have linear data and affine regression data. And we can see the more difficult the task actually gets, so moving from here to the other corner, we can see actually that evolutionary search is actually able to outperform random search. But we can also see that it's rather hard to find good architectures using random search now and rather complex approaches, especially here where we want to search for the complete pipeline. So what the AutoML 0 paper is also showing that we need thousands of CPU hours in order to actually find a very simple neural network, with the downside that we start from the very beginning from scratch. So actually showing that it's very hard to search within very large search spaces in a very reasonable amount of time. So AutoML 0 is the first step towards large and expressive search spaces, but it requires huge time budget to find a simple network being able to perform very well on, for example, something like Cypher10. What we actually want is a search space which is expressive enough to contain a diverse set of architecture, which is not too large that search slows down too quickly and too much which is actually happening in AutoML 0. And exactly that is what we will look at now. So in general, what we view architectures are as computational graphs, where here, for example, we have our edges being kind of the attributes of the actual operations. So the operations are here kind of primitive computations, convolution, skip connections, or a linear layer. Or, for example, a computational graph itself. And so here we can see an architecture with two kind of residual blocks followed by a linear layer. And we have a predefined merging operation at these kind of nodes. And in general, we can see that this example can be also represented as a computation of a multivariate function. So we have our first residual block, which contains of a convolution, a skip connection, and convolution. We have our second residual block, and then we have our linear layer. So we have here multivariate functions. And what we can also do is to distinguish between these types of function using a topological function, for example, saying that is a residual block, and primitive computations, for example, a convolution, or here a linear layer, which eventually leads to the overall composition as a function, saying we have our sequential, we have a residual block, which is our topological function. We have again our topological function and the computational primitives in between. That is kind of giving rise towards a new area of how we can design search spaces using context-free grammar. So we have seen now we can use text more or less and a composition of functions to represent neural networks. And so the idea in context-free grammar is to generate language that hierarchically can be composed from an alphabet, where our graph now is a tuple of 4 different parts, with n being a finite set of non-terminals, capital sigma being a finite set of terminals, R being a finite set of all production rules, where the production rules just means that a rule mapping from a non-terminal to a string of another terminal or non-terminal. And then we have capital S, which is kind of our start symbol with what we start. And in general, the idea of how we can therefore generate a string is we start with our start symbol S, and we recursively select the production rule until the resulting string does not contain any non-terminals anymore. So therefore, context-free grammar is based on text, which we can then use to actually present a neural network. And one example can be seen here. So we start with S being kind of a non-terminal. Our terminals are convolution, the skip connection, ID, and a linear layer. And we have our production rule, which is defined by that, which kind of decides what could be potential options to replace S. And the options are always divided by vertical bars here. So we can replace S by either a sequential, using again some symbols S. We could use a residual with S. We could use a computation of convolution, a skip connection, or a linear layer as the computations itself. So each S itself can be recursively expanded. It could be, again, another sequential, a residual, all these 3 different types of computations. So for example, what we could say is that we use our first S, replace it with a residual, having again 3 different types of S, resulting in the first part of our neural network, which we can see as a graph view here, our 4 edges, SSS, and then deciding that the first S is the residual, resulting in an overall graph view. So we expand the first S as a residual, and then we can expand the residual using, for example, any kind of terminals, using convolution or the identity or a linear layer. And what we want to now present is kind of the hierarchical Nussbench 201, which uses the context-free grammar, which we have seen on the slide before, in order to design a complete neural network. So having the set of potentially infinite function compositions, which can be generated by the context-free grammar tuple, which is then our graph, using language can be used as a search space, with the goal again to search for a grammar which minimizes the loss for some data, as we always do in neural architecture search. And so this paper by Simon Schrodi et al. From 2023, also from the University of Freiburg lab, actually decides how we can define a search space using grammar. So this paper proposes a hierarchical extension of a cell-based search space called NASBench 201 that additionally allows to search for macro topology information as well as parameterizations of the convolution blocks. So for in cell-based searches, we always assume that the convolution blocks are predefined, what kind of activation function, for example, we use. Here we can search for different types of convolution, different types of activation, as well as different types of normalization. So in NASBench 201, we normally say we have a, for example, 3x3 convolution, a batch norm, and a ReLU. So these things are fixed, which are then defined as the convolution operation. Here we search for the activation as well as the normalization all together with the block as well as the macro topology. So here the blue parts are the non-terminals, which construct kind of the macro topology with flexible spatial resolution and also allow for multiple branches. The parts CL and OP, capital CL and capital OP, are also non-terminals, and these are from the original NASBench 201 paper. And with the decision of here we have our cell, here we have our operations, where the operations can be then again some zero, a skip connection, a pooling with the convolution block, again for the question which convolution blocks we actually want to use. And here the question of allowing for to parameterize the convolution block of saying we have an activation, we can search for the convolution type, ranging from 1x1 convolution to a 3x3 convolution, or here a dilated convolution, and what kind of normalization we want to use. A batch normalization, which we do in the original NASBench 201 paper, or kind of, for example, a layer norm. And also allowing for different activations functions. So everything which is yellow is kind of new in this hierarchical NASBench 201. This search space in general, based on the definition of what we have seen on the slide before, provides us with 10 to the power of 446 different architecture. However, these architectures are all CNNs. Therefore, we want to go on the next slide to a new search space called Einspace, which was presented by Erickson et al. In 2024, which is also based on context-free grammars. And this search space unifies different network families. So it allows to search for convolution neural networks, transformers, or also MLP only, as well as any kind of hybrid versions. So let's go now into the next search space. So the Einspace search space starts with categorizing fundamental operations in 4 different groups. So the first group is a branching group, which is kind of a one-to-many function, which kind of which splits or clones a tensor. So it's a function that directly looks at the flow of any kind of information for the network by cloning or splitting a tensor. One example could be a self-attention module where we want to change one tensor to query, keys, and values. This branching operation can be seen here in yellow, also here in that macro structure, in that example from the paper itself. The second fundamental operation which this paper proposes is an aggregation function, which is kind of a many-to-one function that merges the information from multiple tensors into one, which could be matrix multiplication, addition, concatenation, summation. This is seen as purple, or this is symbolized and visualized as purple. The third fundamental operation is a routing operation, which is a one-to-one function that just changes the shape or the order within the tensor without actually alternating its information. This could be axis permutations as well as functions into color or culture operations, and these are visualized by the color green. And the last a fundamental operation is actually the computation one-to-one functions that alter the information to of the tensor. So the routing does not alter the information, it just changes the shape or the order. The computation actually alters the information, either using a parameterized operation, a normalization, or or some nonlinearity. So a linear function, activation, positional encoding, batch norm, softmax, all these things, for example. And visualized are these fundamental operations by the color blue. So having now these fundamental operations, we actually want to look into how the search space is defined. And that is defined by using a context-free grammar, with here uppercase symbols being non-terminals. So these can be combined then with lower cases being terminals, where actually the sentence or the grammar ends, the string ends. So the groups we just saw kind of describe the fundamental operations that can make up an architecture. But now we need to figure out how can we use these operations and compose them in order to actually generate an architecture. And what Einspace is actually proposing is to use different kinds of module, which are defined by a composition of those functions, taking in a tensor, so having input tensor and producing an output tensor. And there are in total 4 different modules, which we'll look at now. So we have our starting module S now. And our first module is a sequential module. So we could go from a module to 2 modules, which is a pair of modules or functions which are applied to the input in a sequential manner. We have a second module, which is a branching module, which first splits our input into multiple branches, and each branch is then processed by some module or function again. And what's very important here, that a branching module is always combined with an aggregation function, because the output of the branches are then merged together using this aggregation function A here. The third module is a routing module, which is defined by a routing function, which follows then again any kind of module or function, and again a final routing is processed on the in order to actually generate the output tensor. So the functions are based on the computational function we have seen on the slide before. And then we have kind of the last module being C, which are then just like the computations, which are only single functions, for example, the identity, the linear layer, normalization. So for each of those modules or calculations, we can see different examples here. So for example, branching means we can clone or group things together. Aggregation means we do some math multiplication, adding or concatenation. Our routing functions P and R, depending on if we are at the beginning of the module or at the end of the module, can be an identity, can be an image to color or column to image, or a permutation, or the computation itself being the identity or any kind of different computations. So these parts are all making up the overall Einspace search space, which we can use then to search for different operations or different networks in general. So in general, I'm not going too deep into the actual computations, but just wanted to present what kind of search spaces we can use, going beyond pure cell-based search spaces, now allowing for actually context-free grammar. So designing a neural network by context-free grammar, so by text in general, which allows for very versatile architectures. However, based on how we design the context-free grammar search spaces, can only look at convolutional neural networks or also on hybrid versions of convolutions to transformers or MLPs. So therefore, the most important insights from this video is that newer NAS approaches aim for expressive search space. So these papers came out in the last years, so very recent, which are still in development. How can we actually properly search within those search spaces? Because, for example, the Einspace search space actually is an infinitely large search space. So therefore, this also allows for the possibility of finding novel networks and allows for better studies and improvements of the actual search, overcoming only using random search in very narrow search spaces. So thank you very much for listening, and that was the NAS part.